Welcome back to Calculus 3. Hey, we are getting to 5.3, but anyway, still it is double integrals. Double integrals in polar coordinates. Remember previously we have double integral over rectangular region, and then we have double integral over type 1 and type 2. And also I want you to know, many times you may have a region which cannot be considered simply as type 1 or type 2. Like you have region involving with circles, circular sections. Okay, so this is the circular section I'm talking about. Basically, it is part of the rings bounded between two circles, but not the entire ring. Okay, it is the angle running from alpha to beta. And the radius of circle, for the smaller one, that's A. For the big one, that's B. And circular section. And in this case, you really cannot consider this as type 1 or type 2. Besides, it would be very hard if you divide into multiple regions. Okay, but we know when we have circles or circle-related things, polar coordinates would help. So indeed, for a circular section like such, we always can use polar coordinates to describe the region. So the region in terms of polar coordinates, somewhat they are bounded by two constants. Remember in polar coordinates, we always use r and theta. So r is bounded by two constants, theta the same situation. And then you may wonder what would happen to the situation we have double integral over a region like this. And then, as I'm saying, it could be evaluated using polar coordinates. Okay, first you are going to replace x with r times cosine theta. That's all about polar coordinates. Y with r times sine theta. So hopefully this entire function is converted into r and theta. Then the dA part, remember for type 1, type 2, or even for the rectangular region, it can be either replaced with dx, dy, or dy, dx. Then when you are using polar coordinates, I want you to know this dA part, it is replaced with dr, d theta, but it does come with this extra r. Don't forget the extra r outside the parentheses when you evaluate a double integral using polar coordinates. Polar coordinates usually will handle a shape or region involving with circles very well, especially for a circular section. For a circular section here. Okay, don't forget this extra r in the middle here. This is different from the rectangular coordinates. This extra r, it is always there. As I'm saying, you do want to consider dA is replaced with r dr d theta. dA, it is replaced with r dr d theta. How about let's work on one example. Actually, I believe I have two examples from 5.6. Well, example 5.6. The topic it is from 5.3. Okay, we want to evaluate this double integral, but the situation here, the region, it is a unit circle. And I hope you understand unit circle still will fit the situation as I just mentioned. Even though we only have one circle, we can consider the smaller one, it is of radius 0, right? So it just reduced to the origin. And then we have the entire circle, so the angle is changing from 0 to 2 pi. So this is what I did first. I realized the unit circle can be represented using polar coordinates in I say in a very simple fashion. Okay, no square roots, no power of 2 at all. That is the polar coordinate representation for a unit circle. And also in polar coordinates, as I mentioned earlier, x is r times cosine theta, y is r times sine theta. So accordingly, x squared plus y squared equals r squared. It's always true. So I'm saying, especially for this part, x squared plus y squared equals r squared. I'm saying, look at the integrand. the function inside the integral notation, that's integrand. I'm saying I should highlight negative x squared and negative y squared together. Would it just be negative r squared? So that's what I did. 1 minus x squared minus y squared, simply it is replaced with 1 minus r squared for polar coordinates. Then dA, it is replaced with r dr d theta. R dr d theta. Okay. dA, it is replaced with r dr d theta. And then in terms of r and theta, these are very simple integrals, right? 1 minus r squared times r. Really, this is r times r minus r cubed. So accordingly, the antiderivative, it is 1/2 r squared, and then minus 1/4 r to the 4. You're going to evaluate this expression when r is 1 for the upper bound, and when r is 0 for the lower bound. R is 0, easy. The entire thing just turns to be 0. When r it is replaced with 1, it's just 1/2 minus 1/4, right? So that's 1/4. And then for the outer integral in terms of theta, indeed, it's just 1/4, antiderivative 1/4. So it is 1/4 times theta. And theta, it is replaced with the upper bound 2 pi, lower bound 0. So I'm having this answer as pi over 2. I say this should be a very simple example. And also, I hope you understand the situation very well. I'm saying in general, when you look at this double integral, you really don't expect anything about pi at all, right? If you are going to use rectangular coordinates, you cannot get the answer because mostly I don't see any point. I don't see this pi will pop out any point anywhere from the rectangular coordinates. But anyway, indeed the answer is pi over 2. And indeed, if we use polar coordinates, I say the double integral, it is handled in a very easy and efficient way. Okay, so again, to evaluate a double integral using polar coordinates, make sure you do understand the conversion. And this property, it is also very helpful. Not always, like in this case, we do use this property. And also for the dA part, dA really has to be replaced with r dr d theta together. Especially, I want to emphasize the extra r. And I do have this extra r here in this evaluation here. How about do one more example using polar coordinates? And still, the double integral, it is given in the in the rectangular coordinates form. And then the region, actually, how do we expect this type of region? I'm seeing x squared plus y squared will have to be something about circles, right? Circle centered at the origin, and less than or equal to 4, it will be the circle of radius 4. Greater than or equal to 1, it will exclude the circle with radius 1. So it is a ring-shaped thing. It is a ring. It is a ring between, it is a washer between between two circles. And also don't forget the second part, it says x is always negative. Without this part, I'm seeing the ring between two circles because x has to be negative or 0 is included. So we are having half of the ring to the left. That's all for all those negative x values. Okay, so I say this is a circular section, right? The circular section I'm talking about here, it's like this. Okay, and so according to using polar coordinates, we can describe this region into this fashion. R and theta. R is changing from 1 to 2. This is 4, it is 2 squared, right? And the theta, do understand the angle correctly. All the way to y-axis, from x-axis to y-axis, that's pi over 2. Then all the way and move to the other side of axis, that's pi. And then move to the opposite of y-axis, that's 3 pi over 2. So theta is changing from pi over 2 to 3 pi over 2. By the way, I should have mentioned that when you use polar coordinates, the angle, it is always in the radian measurement. You cannot use angles. You cannot use degrees. I'm sorry. You cannot use degrees. It will have to be, the angles will have to be in radian measurement. You cannot use 90 degree, 180 degree, those things. Got to be radians. Okay. And then to evaluate this double integral, I'm using polar coordinates. So r is replaced with, x is replaced with this. Y is with r times sine theta. Then dA, remember dA does have this extra r dr d theta. Okay. And then when I evaluate this integral, I guess maybe we factor out this r first. R times another r, that's r squared. So the integral in terms of r with respect to r, that's 1/3 of r cubed. At this moment, cosine theta, sine theta stay as they are. Okay. And then I'm replacing r with 2, and replacing r with 1. Then according to the fundamental theorem of calculus, you take the difference of the same expression for those two different values. So I believe it should be 7/3. 1/3 r cubed. That's 7/3. Okay. Then antiderivative this last round, out round of integration with theta. Antiderivative cosine theta, that's sine theta. Antiderivative sine, that is negative cosine. So you plug in those angles, and well, I'm going to leave that for you to verify. I think it should be all right. Sine of 3 pi over 2, that's -1. And then sine of pi over 2, that's 1. But anyway, it's -1 minus 1. Do you know why I did not mention about the cosine? Because cosine of 3 pi over 2, cosine pi over 2, they both are 0. So I believe this answer should be all right. Okay, so I think for now, I think that should be the material of polar coordinates in section 5.3. Double integrals in polar coordinates. We always can, if we have a region involving with circles, usually it is a good idea to describe the region using polar coordinates. And then conversion from rectangular to polar coordinates, don't forget those two formulas. And also don't forget the special property, and especially for class purpose, many times we are just going to test your knowledge of this trigonometric or Pythagorean identity. Okay, really this is the Pythagorean identity here. And that should be it about section 5.3. Thank you for watching.